morning to one and all. This is Suresh Madineni. My register number is 20BQ5A0409. I am from VVIT College, second year, section 3. Today I am explaining about the square law modulator. The square law modulator having the mainly square law device. The square law device, here the V1 of t is the input of the square law device, and V2 of t is the output of the square law device. V2 of t is equal to A1 V1 of t plus A2 V1 square of t. Here A1 and A2 are constants. In this square law modulator circuit, here the adder or summer, square law device and band pass filter. Finally we get the output of the band pass filter is the modulated conventional AM signal. Here M of t is the arbitrary message signal and C of t is the carrier signal. Therefore the output of the adder is V1 of t. Here message signal is an arbitrary signal and carrier signal is equal to AC cos 2 pi FCT. Here V1 of t is the output of the adder circuit and this is M of t plus AC cos 2 pi FCT. This is taken as equation 1, and V2 of t is equal to A1 V1 of t plus A2 V1 square of t. This is taken as equation 2. So we substitute the equation 1 in equation 2, then we get V2 of t is equal to A1 of M of t plus AC cos 2 pi FCT plus A2 of M of t AC cos 2 pi FCT whole square. Here A plus B whole square formula is used. Then we can expand into A1 M of t plus A1 AC cos 2 pi FCT plus A2 of M square of t AC cos 2 pi FCT plus 2 M of t AC cos 2 pi FCT. A1 M of t plus A1 AC cos 2 pi FCT, A2 M square of t, A2 AC square by 2 of 1 plus cos 2 pi FCT, 2A2 M of t AC cos 2 pi FCT. So finally we get the 6 components of V2 of t. These 6 components will be passed through band pass filter. Finally we get the modulator signal. Let us we know about these 6 components. A1 M of t, this is message signal exists from minus omega to omega. A1 AC cos 2 pi FCT, this is an carrier component exists at FC center frequency. A2 M square of t, this is exists at minus 2 omega 2 plus 2 omega. A2 AC square by 2, this is a DC term, the frequency is 0. This is exists at where F is equal to 0. And A2 AC square by 2 cos 2 pi 2 FCT, this is the harmonic of carrier signal exists at 2 FC. 2A2 M of t AC cos 2 pi FCT exists at M of F minus FC to M of F plus FC. The frequency domain representation of these 6 components is drawn here. This is the frequency frequency domain representation of these 6 components. This is the component 1, 2, 3, 4, 5 and 6. Here the output of band pass filter is we get only desired center frequency is FC and bandwidth of band pass filter is 2FM maximum, and FC carrier frequency is far greater than 3FM. Then we get these desired 2 and 6 components. Otherwise we did not get the output. Here the output of band pass filter is A1 AC cos 2 pi FCT plus 2A2 M of t AC cos 2 pi FCT. Here we get A1 AC is common, then we get A1 plus 2A2 by A1 M of t cos 2 pi FCT. Here A1 AC considered as AC prime and 2AT A2 by A1 is considered as Ka. Ka is equal to amplitude sensitivity. Then we get finally AC prime of 1 plus Ka M of t cos 2 pi FCT. The second one is 4-bit prime number detector. Here inputs is taken as 4 bits N3, N2, N1, N0. The output is 2 power n combinations, that equal to 2 power 4, that equal 16 combinations. We get 0 to 15. Here the prime numbers are 1, 2, 3, 5, 7, 11, 13. These are between 0 to 15. And here the output is which number is a prime number. then we output is taken as high. The number which is not a prime number, we taken the output as low. By using K-map, we can solve this, and finally we get f is equal to n3 bar n0 plus n3 bar n2 bar n1 plus n2 bar n1 bar n0 plus n2 n1 bar n0. By using this equation, we extend into a logic circuit. The logic circuit having a 3 NOT gates, 4 AND gates and 1 OR gates. So here we having a 7 signals, x1, x2, x3, a1, a2, a3, a4. Then we use a VHDL code for this logic circuit. Is first we write what library we used. Here library packages are written, and next entity declaration, and next architecture formation. Here first one is library IEEE. Use IEEE.stdlogic 1164.org. Entity declaration is entity prime. Here entity name is taken as prime, is port n colon std logic vector 3 down to 0. Here 4 bits are taken, then we write 4 down to 0. F is output std logic, end prime. Here end entity name. Architecture name of architecture of entity name is, here architecture prime 1 of arc of prime is signals. The signal declarations are is given here. Signal declarations x1, x2, x3, a1, a2, a3, a4 colon std logic. Here begin x1 is less, here equal to is not used to, less than or equal to is used as a equal to, not of n of 3, x2 is less than or equal to not of n of 2, x3 is less than or equal to not of n of 1. Here a1 less than or equal to x1 and n of 0, a2 less than or equal to x1 and x2 and n of 1, a3 is less than or equal to x2 and n of 1 and n of 0, a3 is less than or equal to x2 and n of 1 and n of 0, a4 is less than or equal to n2 of n of 2 and n x3 and n of 0 colon f. Finally output f is less than or equal to a1 or a2 or a3 or a4 colon, end architecture name prime of. This code also written by using the selected signal assignment statement. Therefore the prime number detector using the selected signal assignment statement. Here using library and packages and entity declaration and architecture formation. Here library IEEE colon use IEEE.stdlogic 1164.org. Here entity prime is the entity name, and port n in is used as input, std logic vector 3 down to 0, f out, std f is the output, end prime. Architecture prime arc of end of prime is, here architecture name of entity name is begin with, by using the statement of with n select f less than or equal to 1 single colon when double colon of 001. Here whatever the outputs is high, these outputs are selected as 1. Whatever the outputs is low, these outputs are selected 0 when others. So when these numbers are get, when the output is high, therefore these output high is taken as prime numbers, and 0 is it doesn't takes, end prime arc. Third one is the standard test signals from controlling systems. The test signals are used to test the performance of a controlling system. The characteristics of a test signals are sudden change, sudden shock, and constant velocity and constant acceleration. Here the 4 basic test signals are there. They are step signal, ramp signal, parabolic signal, and impulse signal. The step signal is also known as sudden change. Here the step signal having a sudden change in amplitude. When t is greater than 0 or equal to 0, the step signal is high, taken as high. When t less than 0 is taken as low. Therefore the amplitude is suddenly changed from 0 to a. So therefore the r of t is equal to a into u of t. Here the Laplace transform of the step signal r of s is equal to a by s. And the second, this step signal is very useful in testing of a controlling system. When this amplitude is when this step signal is given to the input of a controlling system, the amplitude of the step signal is suddenly changed. Then the how the performance of the controlling system is evaluated by the step signal. The second one is the ramp signal. The ramp signal having constant velocity. Here the amplitude of the signal is linearly vary with respect to time. So here the ramp signal is given to the input of the control system. The control system how the response to the linearly varies time. Here r of t, at is equal to t greater than or equal to 0. When t is greater than or equal to 0, then we get at 0 when t less than or equal to 0. Therefore the Laplace transform of r of t is r of s is equal to a by s square. The ramp signal is used to test the ability of the system how evaluated or linearly varies with respect to time. And the third one is the parabolic signal. The parabolic signal having a constant acceleration. This is one time faster than the ramp signal. Here the r of t is equal to 80 square by 2 when t is greater than or equal to 0. When t less than or equal to 0, 0. Therefore the Laplace transform of r of t is equal to a by s cube. And this parabolic signal is used to test very fast than the ramp signal. And the fourth one is the impulse signals. The impulse signals is the delta of t infinity when t is equal to 0 infinity, otherwise t not equal to 0 0. Therefore the integral of impulse t minus infinity to infinity impulse t dt is equal to 1, and the Laplace transform of impulse signal is equal to 1. This way 0 when t is equal to 0 is equal to 1 when otherwise it is 0. Here the differentiation of parabolic signal is given as ramp signal, and the differentiation of ramp signal we get the step signal. Differentiation of step signal we get impulse signal, and in reverse order, integration of impulse signal we get step signal, integration of step signal we get ramp signal, integration of ramp signal we get